Welcome to The Explainer. Today, we're going to break down this absolutely brilliant idea, a mathematical tool that lets us measure what seems, well, unmeasurable. Let's jump right in. All right, so let's start with a puzzle. A puzzle that's bugged mathematicians for forever. Squares, triangles, that stuff's easy, right? You've got formulas, but look at this thing, this curvy, weird, unpredictable shape. How on earth do you even start to figure out the area of that?
So to figure this out, we're not going to start with some crazy, complicated formula. Nope, we're going to start with a really simple idea that I think you'll get right away. Approximation. Okay, so first attempt. Let's just stuff some big, chunky rectangles under there. We know how to measure rectangles, so why not? But yeah, as you can see, it's a pretty awful estimate. You've got these huge gaps, places where it overshoots. It's just not going to work. Not even close.
But what if we try something else? What if instead of a few fat rectangles, we use a ton of super, super thin ones? Now look at that. All of a sudden, our approximation gets way, way better. Those gaps are almost gone, the overlaps are tiny, we're getting really, really close to the actual area.
So, you know where this is going, right? Let's take that idea to its logical extreme. Imagine a rectangle that's infinitely thin. So thin it's basically just a line that has a height. This right here, this is the big leap. It's the idea of an infinitesimal slice, our perfect little building block. Okay, but that kind of creates a whole new problem, doesn't it? If we have an infinite number of these infinitely thin slices, how in the world do you add them all up? You can't just count them one by one. For that, we need a special tool.
And that special tool, it's called integration. You see that symbol, that long S shape? It's basically a fancy S for sum. Seriously, think of it like the ultimate adding machine. It's built for one very specific, very cool job, to add up an infinite number of those tiny, tiny slices perfectly. It gives you one single exact number for the total area, no more estimating. Now, using a tool this powerful isn't always super straightforward. There are a few, let's call them quirks or traps, we need to look out for, especially when our shapes start to misbehave a little bit.
For example, what happens when our nice curve decides to dip below that main horizontal line, the x-axis? Does that area just not count? What do we do with that? So here's a really interesting quirk. The math itself, it actually sees any area below that main line as negative. Which is weird, right? You can't have negative area in the real world. So we have a simple rule. We just calculate it, see that negative sign, and we ignore it. We just take the positive value, because we're talking about actual space. Easy fix. So the big lesson here is, if your shape crosses that line, you can't just do one big calculation and call it a day. You have to treat it like two separate problems. You find the area of the top bit, you find the area of the bottom bit, you make sure they're both positive, and then you add them together. That gives you the true total area.
Okay, so let's take this a step further. This is where it gets really cool. What if the area we want isn't under one curve, but the space that's actually trapped between two completely different curves?
The way we solve this is just so elegant. First thing you do is pretend that bottom curve doesn't even exist. Just ignore it. You use integration to find the entire area under the top curve all the way down to the axis. Next, you do the exact same thing, but for the bottom curve. You calculate all the area that's tucked underneath that one, again, all the way down to the axis. And here's the magic. You just subtract that second, smaller area from the first, bigger one. And poof, that whole bottom section they both shared just cancels out. What's left behind? The exact area you wanted, the space trapped right between those two curves. It's so clever, like a perfect little bit of mathematical surgery. Look, I know this can all feel like a pretty abstract math puzzle, but I promise you this one idea, finding the area of these weird shapes, it's one of the absolute cornerstones of modern science and engineering. And trust me, this is everywhere. You want to figure out the lift on an airplane's wing? Well, that's just the area between the curve on the top and the curve on the bottom. You want to model how water flows or how much stress a bridge can take or even predict financial markets. Yep, it all boils down to this one powerful idea, summing up an infinite number of tiny pieces to understand the big picture. It's just such a powerful reminder, isn't it? Sometimes the biggest, most impossible-looking problems can be solved if you just find the right way to slice them up into tiny, manageable pieces. And that makes you wonder,
If integration can let us measure any shape, what other supposedly unmeasurable worlds can we start to calculate?